This meeting is being recorded.
In this video on section 15.4, we're going to talk about the first type of information that we were told can be revealed from an NMR spectrum. So the number of signals. This will tell us how many different kinds of protons are in a compound. So when we refer to this different kinds of protons, we're specifically saying the different chemical environment or what is next to each of these protons. So if they are chemically equivalent, we would say that they have the same chemical environment. And a way of referring to this is that they are homotopic. So if they are protons that would produce a single signal, they would have the same chemical environment, they are chemically equivalent. These would be referred to as homotopic protons. We can also see enantiotopic protons, and we can differentiate between the two. But remember that these homotopic protons, these would all produce the same signal. So a way of defining these is if they have an axis of rotational symmetry. So let me try to show that here. With this first molecule, these two red protons would again be homotopic, and if we were to draw this axis of symmetry here and then rotate along that axis of symmetry, say you closed your eyes, did the rotation, and then opened them, you could imagine that you couldn't tell which proton was which. So due to that, we have this axis of rotational symmetry, and we wouldn't change. So without changing the molecule. So when you open your eyes, poof, same molecule. So let's take a look at, say we have an axis of symmetry this way here, and we rotate it in this direction here. So again, close your eyes, rotate the molecule, open them, and everything looks the same. So again, these two protons here on this difluoromethane, this would be two homotopic protons. And the same thing would occur with this cyclopentane here. So, or cyclopropane rather. So say we rotated this along this axis of symmetry, opened our eyes, we wouldn't be able to tell which proton was which. So that's the easiest way to designate if you have two protons that are in the same environment, if you can create this axis of rotational symmetry. So another test is to replace one at a time. So replace one proton at a time, and we could see that if we have an identical compound that's created, like we do over here, if we replace either of these protons with a deuterium here, so we have D instead of H, we see that we have identical compounds, so therefore we confirm again these protons are homotopic and identical. Same environment, they would produce the same signal. Now say we have enantiotopic protons. So if a molecule now has a plane of reflection, not an axis of symmetry, but rather a plane of reflection where one proton is the mirror image of another, we would refer to these as enantiotopic protons. Just like when something is a non-superimposable mirror image of itself, we refer to that as its enantiomer. So it's hard to draw slicing these molecules in half, but if you could imagine that we have a plane of symmetry, which is the plane that these molecules are in, therefore we would have these two protons in slightly different environments, as would these two protons over here on this cyclic structure. So these protons are therefore referred to as enantiotopic protons, and generally if there is a chiral center, you would want to check for those. We can also apply this replacement test where we replace one hydrogen and then another. So you can see over here we have deuterated this compound, and we could imagine that we have our mirror image reflection here, and these two compounds are enantiomers, so therefore we refer to these as enantiotopic protons. So we want to, again, determine the number of signals based on symmetry. So to determine if our protons are equivalent, first we would look for rotational symmetry. So we'll start up here and we'll say, okay, is there an axis of symmetry? So if yes, then we would say that we have homotopic protons, which are chemically equivalent and would produce one signal. Then we could look again and say, if no, there's no axis of symmetry, we can check for a plane of symmetry. And then if yes, then we have those enantiotopic protons, which would also be considered chemically equivalent and produce that single signal. But if we have neither an axis of rotational symmetry or a plane of symmetry, then that brings us over here. And we could finally say, no, these are not chemically equivalent protons, and they would produce separate signals. So if our replacement test produces diastereomers, we could call those protons diastereotopic, and therefore we know diastereomers, these would not be chemically equivalent. So again, we can use that single replacement test, replace one of those protons at a time, that's in question. And we would see that these would be, again, not chemically equivalent. Diastereomers result, so these are diastereotopic protons. So again, if we go to our flow chart and we decide that we do not have homotopic nor enantiotopic protons, then we would consider these chemically distinct, not chemically equivalent. So let's take a look here at our 2-butanol. So this is the structure of our compound 2-butanol. And we can see that on this wedge here, we have this hydroxyl group. So this proton that is on this wedge would have a different chemical environment than this proton that's on a dash. It's not in the same plane. So because these protons cannot be interchanged by rotational symmetry or reflectional symmetry, we would note distinct signals. So these are, again, not chemically equivalent protons in this compound. So there are some ways to lessen the amount of time, create some shortcuts when you're looking at compounds. So as I mentioned before, when there is another chiral center, we can say that generally there may be a CH2 group that does not have chemically equivalent protons. So that's what we see over here. So this is the rationale for 2 listed here. So 2 protons in this CH2 group, these will not be equivalent because we have another chiral center. But looking over here for consideration 1 here, if the 2 protons are on a CH2 group rather, so we have these 2 protons on the same carbon, they would be considered chemically equivalent if there are no chiral centers in the molecule. So again, this is a shortcut that you can use when considering, are these going to be enantiotopic or homotopic protons versus not chemically equivalent diastereotopic protons. And we have another shortcut shown here. So 3 protons on any methyl group will always be equivalent. So anytime you see CH3, right, all these protons are equivalent. And if we have multiple protons that could be interchanged either through a rotation or a mirror plane, so in this case, we could exchange these or interchange these protons through both, right? Either a rotation or a mirror plane. So all 4 of these protons, we would see produce one single signal. And that's because they are all chemically equivalent. So again, if you look for rotational axes of symmetry or planes of symmetry, that can shortcut your determination if you're going to see 1 or more signals. Again, it all has to do with our chemically equivalent environment. So that brings us to cyclohexane, and we know that there are two types of protons because we looked extensively at our ring structure here, cyclohexane. We know that there's 6 equatorial and then there's 6 axial protons. And we should see 2 distinct signals, but at room temperature, generally there's only 1 signal observed. So that's because these 2 protons are being interconverted at room temperature. So this occurs rapidly, and we can see this red proton was axial, now it's equatorial. So we can see this ring flip occurring at room temperature and only 1 signal produced. But if we lower the temperature drastically down to about negative 100 Celsius, the ring flipping is slowed down enough that we could observe 2 distinct signals. So we'll talk about the location now that we've reviewed how to determine the number of signals based on the number of chemically distinct protons. Then we'll look at where the shift would occur in our next video.